Hello students, welcome back to a new video on the topic of work per energy. It is the second chapter for the exams, and in today's video we will be only focusing on the topic of work. So what is work? What is work? The simplest definition is when a force causes a displacement. When a force causes a displacement, a work is said to be done. So with the simplest definition, the formula will be W equals to F into S, where F is the force and S is the displacement. Okay, the simplest format. For example, here is a body. I am applying a force of, let's say, let's say 10 Newton, and the body moves forward by a distance of 10 meter from point A to point B. So according to the formula, we can say that the work done to move the body from point A to point B is 10 into 10, that is 100, and the unit is joule. The unit of work done is joule. Okay, so just go through it. So now let's move over here, that unit of work. Now see, since W equals to F into S, we know that the unit of force is Newton and for displacement is meter. This too becomes the unit joule, that is J. Okay, so that is the SI unit. So SI unit of work done, I am writing work done in short form as WD, is joule, and CGS unit of work done is erg. Now you all should remember the interconversion between joule and erg. 1 joule is equals to 10 to the power 7 erg. 1 joule is equals to 10 to the power 7 erg. Now how does this come? Let's do the conversion. Conversion from joule to erg. So 1 joule is 1 Newton into 1 meter, and 1 Newton is 1 kg into 1 meter per second square, and this meter is 1 meter. Now converting everything into its CGS unit, 1 kg is equals to 1000 gram, 1 meter is 100 centimeter per second square into again 100 centimeter. This too, that is 10 to the power 5 gram centimeter per second square into 100 centimeter, sorry. This too is your dyne. So this is 10 to the power 5 dyne into 100 centimeter, and then It's 10 to the power 7 dyne centimeter, which is equals to 10 to the power 7 erg. That is the complete conversion from joule to erg. Okay? So, now let's move to the next topic, that is, we have just discussed that when force is applied in a certain direction of a body, it moves a certain distance s, then work done equals to F into S. Perfect, no problem in that. But what if the force acts at a different angle than the displacement? For example, let's say our body is like this. The displacement is taking place in this direction, whereas the force is given in a certain direction. The angle between both of them is, let's say, something theta. In this case, the work done formula becomes Fs cos theta. Fs cos theta. And that's why this Fs cos theta is said to be as the actual formula of work. This is the actual formula for work, W equals to Fs cos theta, because this formula goes with all the conditions. Now, we will take each condition separately. For the first condition, let's assume condition number 1. Let's assume a body is at point A. It has to move a distance s in this direction to point B, and the force is applied in this direction. So according to the formula, what is the theta first of all? Now, when force and displacement are on same side like this, force and displacement are on the same direction, then theta is 0 degree. Theta is 0 degree. So using this concept, your work done will be equals to F into S into cos 0. And cos 0 is 1. Therefore, work done equals to Fs. In these cases, we say that maximum work is done. Maximum work is done. Okay? Now, let's take condition number 2. Let's say a body is rotating in a circular path. Let's take it. This is the point A. This is the center part. Let's take at O. It is tied through a rope. It is tied through a rope. There is a tension force acting towards the center. This is known as the centripetal force. Those who don't know what centripetal force is, I would request you to go and see my first video on the previous chapter, force, to get a proper idea what is centripetal force. And the body's displacement is in this direction. So in this case, you can clearly see that there is an angle formed between the displacement and the tension, and the theta value is 90 degree. The theta value is 90 degree. So using the formula W equals to Fs cos theta, if you put W equals to Fs cos 90, we know that 90 is 0. So the work done equals to 0. Means no work has been done. That's why we say that when a body is rotating in a circle, work done is 0. Now there are two ways to confirm this. One, if the body completes one complete revolution or one complete rotation, it's going to come to its initial point. So initial point and the end point is same, and physics says that displacement in this case will be 0. Starting point and ending point is same, so displacement will be 0. In that case also, if we take that W equals to Fs cos theta, now S is assumed to be a 0, so work done is again 0. Why S is considered 0? Because the body is returning to its initial position only. But if someone asks, okay, the body is not returning to its initial position, what will be the work done if the body has completed half circle? Let's say like this. Let's say the body has completed only half circle. Then they will ask you what is the net work done. Now, although the body has completed half circle, but we know that according to basic physics, this was the tension force, the direction of tension, and this was the displacement. Still, the angle between the displacement and the force is 90 degree. At this point, this is the tension and this is the displacement. The angle between them is 90. Now, since angle is 90, according to the formula of W equals to Fs cos theta, so that will be W equals to F into S into cos 90. And cos 90 is 0. So W equals to 0. Okay, so we have many examples of this. For example, Earth revolving around the Sun, work done 0. Electron revolving around the nucleus, work done 0. Another example. Okay, I will just write the examples for you so that you can get a clear concept. Number 1, revolution of Earth, work done 0. Revolving of electron around nucleus, work done 0. A person standing still means he is not moving, work done 0. And another type of questions are mainly asked in boards, that a coolie is carrying a load on his head, work done 0. So there are multiple cases where the work done is 0. The first two cases the work done is 0. The reason is the angle between the force and the displacement is 90 degree. The second two cases the work done is 0. The reason is because the displacement is 0. The person is not moving. So what is the displacement? 0. The coolie is not moving. What is the displacement? 0. So in the first two cases, theta is 90 degree. And the second two cases, displacement is equals to 0. Okay. Now comes the concept. Now let's say in school they ask you that, what if, let's say this is the ground, this is the ground, a coolie is carrying some luggage on his head, is carrying some luggage on his head, and he is moving in this direction. A coolie is carrying some luggage on his head and is moving in this direction with the displacement S. Now the school may ask, what is the work done? Now, for this reason, you have to consider another thing, that the force of gravity always acts towards the center of the earth, Fg. The force of gravity always acts towards the center of the earth. So if we draw the simpler version of this, the force of gravity was acting downward, whereas the displacement of the coolie was in this direction. So what is the angle between the, what is the angle between the displacement and the force? That is again 90 degree. So wherever the force is 90 degree, angle is 90 degree, work done will be 0. Work done will be 0. Now many of you may ask that if that thing happened, that we walk on the road, even we are doing 0 work, then why do we get tired? The reason of getting tired is because we are doing the work against friction. We are doing work against friction, not against the gravity of the earth. But the work against the friction is a very vital point. Now let's take that into consideration. So again, let me draw a simple, let's say this is the ground. Let's say this is a person who is walking in this direction, but the force of gravity is pulling him down towards this direction, and very important, the force of friction is acting in the opposite direction. Displacement, force of gravity, force of friction. Because we know friction acts opposite to the displacement motion. So now if we consider the friction and the displacement diagram, so displacement was on this side and friction was on this side. This is the center point of the person, FO. What is the angle between them? 180 degrees. So work done is equals to F into S into cos 180 degree. Now let me remind you, cos 180 is equals to minus 1. Cos 180 is equals to minus 1. Hence, therefore, work done equals to minus Fs. So the first time that you got is a negative work. The first time you have got is a negative work when the displacement is against the force of friction. There is another example of a negative work, that is a tug of war. All your schools in your sports day, you have played this game, tug of war. Two teams pull a single rope on two different sides. Now, for the team to win, the force is on front side because the other team is pulling me that side and I have to pull back. So my displacement is this, whereas the force is on that side. So they're two opposite. Hence, it's negative work done. Okay. Now, let's move to the next point, that is gravitational work. Now, let's say this is the ground and you take an object from the ground position to a certain height position of height h. So, you are moving against gravity. You are moving against gravity. In this case, work done is equals to mgh. What is m? M is the mass. G is 9.8. If you are taking it in SI system, and h is the height. Okay, that is the work is being done against the force of gravity. Now, in many cases, they may ask you, is the work done positive or negative? When you are moving against the force of gravity, this work done is always negative. This work done is negative. Whereas, if the same body was to come from top to bottom, then the work done would have been again mgh, but this time it would have been positive. So moving up is negative work done, coming down is positive work done. This is known as gravitational potential energy or work done, gravitational work. Many of you may consider this as gravitational potential energy also. Let me write it down over here only. Gravitational potential energy. In many of the books, you may find it denoted by U. So U equals to mgh. Okay, so that is the gravitational potential energy. Just go through it once. Okay, now next. Let's say a body was initially not at ground but at a certain height h1. The body was over here. Initially, the body was over here at an height h1 initially. I take this body from this height to another height. The total height is now h2. So, the net work done will be equals to mg h2 minus h1. That is W equals to mg delta h. The difference of height. This is your delta h. This is your delta h. Okay. Next, how to find work done from a flow force and displacement graph. Okay. How to calculate work from graph. Now, let us assume that a graph of force versus displacement is something like this, a linear graph. And you are asked to find the force, the work done that this object has done, completed. All you need to do is you draw a straight line like this till the x-axis, and you then find the area of this portion of this triangle. So work done will be half into base. What is base? Now, base is, this is 0 and this is S1. This is 0 and this is F. So that is again half into S into F. That is your work done. So to find the work done from a graph, just find the area of that graph with the x-axis. If this graph would have been something like this, let's say the line would have been like this, nothing else, like this. So all you had to do is, you had to draw a line like this and then find the area of this graph. That is something like a rectangle. So work done equals to force into displacement, simple. That is simple thing, work for this. This is because the breadth is the force and the length is the S. That's it, the work done to be calculated from a graph. I hope it's clear to everyone. So with this topic, we complete the work part of our chapter. I would request you to everyone to revise the chapter once so that the next chapter, the next topic, of power and energy will become easier for you. Thank you everyone once again. Please do like, share and subscribe. Have a good day.